All right, everybody. Well, thank you for joining us for our Technically Speaking webinar for September 2025. Today, we're going to be talking about artificial intelligence in waste management. Real fast before we get started, we have a few housekeeping items that we'd like to address. The first being, if you've got questions or thoughts, please put those in the chat, and we'll have a Q&A period at the end. It's going to be, we're shooting for 10 to 15 minutes of Q&A time. So in that spirit, please put questions in the chat, and then also folks could stay on mute until that time as well. That'll let us get through our presentation and some of the interactive stuff. We're going to have a few polls, and then finally, if you'd like a PDH certificate for this 1 hour webinar, we'll have some contact information in the chat as well of who to reach out to get that certificate. So with that, we'll introduce ourselves. I'm Skylar Sorsby. I'm a senior hydrogeologist in one of the New Jersey offices for WSP. I've been in site investigation and remediation in both upland and sediment sites for 7 or 8 years now. I'm a hydrogeologist by training and also one of the data science practice leaders at WSP. And Nasim, go ahead.
Hi, everyone. This is Nasim Pika. I sit in DC, and I'm a senior technical manager for WSP, working in a lot of different emerging topics, from PFAS, one for dioxane, and now to artificial intelligence. Happy to be here today.
Awesome. Really quickly, we'll just give you a brief roadmap of where we're going to go with this webinar. I know if you're joining a webinar on AI at this point in time, you know, the idea of AI has been around for a few years. I think we've all probably sat in on a few webinars on AI. We have an idea of what the topics could be. But I guess what I'm going to challenge you with today is that I think we're going to go in a bit of a different direction with it. So we're going to talk a little bit about what machine learning or AI is, the process behind it to kind of unpack that a little bit, kind of get the gears turning. How might I use this on my particular project? We'll show you kind of a simpler application that kind of covers the full range of the kinds of questions you might ask and answer with machine learning. And then I'll hand it to Nasim to talk about more advanced applications of AI, including computer vision and Internet of Things. And then we'll wrap it up with a quick summary and then some question and answer at the end. So kind of our thesis statement for the presentation here is that AI could be used and is used in kind of all aspects of management of waste. So from initial stages through the end. And we're going to unpack that here as we go along. But first, since this is an AI and machine learning webinar, we're going to talk a little bit about what exactly that is. And there's a lot of definitions out there. A lot of them have to do with neural nets. It has to do with the computer learning. It has to do with those kinds of things. I've found the Oxford Languages dictionary definition to be a pretty good one. So it's the idea that you want it to do something. You're not going to explicitly program it to do that thing. And the mechanism that you use to get it to do the thing is a statistical model. So you're basically taking a statistical model, it finds the patterns, and then it can do the task that you're trying to get it to do. Where this kind of comes from, just for some context, this is another quote I really like. It was essentially, it nucleated as models, basically modeling for an industry without models. So in our industry, that sounds kind of weird, right? You know, we're in environmental, we're in waste management, geotechnical, etc. And our industry on the main has a lot of models, many models, ground models, water models, vapor models, air models, geotechnical models. But if you look over in the tech industry, you know, you have some of these burning questions like, well, what's my customer base doing? What will my customer base like? How are my actions affecting my customer base? And there aren't really formalized models for a lot of those things. So enter machine learning and AI, where you take this kind of rich ecosystem of statistics and you frame your question in such a way that you can answer it with machine learning or AI. And then there you have a model. It's kind of a free form model answering kind of a custom question. So that's why it really took off in tech, and we can borrow and are borrowing the same kinds of principles here. So we'll kind of unpack a little bit more about that now. So another good graphic that I really like, if you tend to look at AI kind of at the surface level, the idea is you put data into AI and you get value out of it. It's kind of the simple view of it. But if you look under the hood, there's a whole process. And the reason I bring up this process is when you're either doing machine learning or AI, or you have someone do it for you, there's a whole process involved, and making sure that whoever's doing it knows about that process, is good at that process, and has the bench strength to deliver on that process is pretty important. So when you look under the hood, there's a few things to be aware of. The first is data acquisition. If you already have a database, some sort of large data platform, that's a good thing, but otherwise you can design one. And where this comes into play for us in this industry, if you have sensor data, if you have discrete sampling data, if you have remote sensing, or even if you get into text data, large document databases, these are all candidates for AR machine learning. But really, you have to make it specific to our industry. Once you have those data, you basically get the data into shape. You use what's called data engineering, and that is basically looking for outliers, cleaning the data sets, making sure it's representative, and then otherwise working on it to get it in the right shape for modeling. Now, for machine learning and AI, a lot of people think, just jump straight to modeling. This is kind of like the coolest part for a lot of people, but it really, in a responsible AI workflow, this is just one part. And the idea here is you've designed the question, you have the data, and this is where you teach the machine to get the answer. And I'm not talking about using ChatGPT to answer questions necessarily. I'm talking about this rich ecosystem of statistical models. So you pick a few based on experience and knowledge of the toolkit, and then you train them, evaluate them. So that's the modeling component. And then at the end, let's say this is for a report, you might need just a simple report, some sort of static thing, which is classic in our industry, but you might want something more interactive too, like a cloud deployment or something on a server. So then that's operationalizing this model that has been trained to answer your questions. So that's the process, and all of these pieces are important. Now, I guess I would argue that most of us have encountered pretty much the full gamut of AI and machine learning questions that can be asked. So I'm going to start in this upper left quadrant and work my way clockwise, or roughly clockwise. So in this upper left corner, we have this type of question here that we often see with valuation of homes. So if you've ever looked for a home on Zillow, a home price is kind of a sliding scale. You can have larger numbers or smaller numbers. It's the value of the home, and determining that value is the geographic location, the size, et cetera, many different features. But really, you're using a bunch of data to predict a sliding scale. So this is something you probably have seen if you've used Zillow or some other home valuation tool, and this is called regression. Now in the upper right corner, this is a similar concept. You have a data set, you have a bunch of predictors, and you're trying to predict a group. So if you've ever used a spam classifier for your email, this is a machine learning model that discerns whether or not the wording in your email is spam-like or not, and it categorizes it as spam or not spam. And the model has been trained on many emails that are spam-like and many that are not. Now, if you go to the lower left corner, for those who use streaming services like Netflix, the way that Netflix makes its recommendation is it records the things that you watch and the things that you like to watch and the things that you don't like. And it compares that profile with what everyone else does, and then basically compares you to, uses correlation essentially to compare you to everyone else, and then make the recommendation. But in this case, it doesn't have a quantitative label. Like for a home price, the home has a price. For a spam classifier, you can definitively say spam or not spam. Now a recommender, like this in the lower left, you don't have labels already, and it's essentially an unsupervised task. This is called dimensionality reduction. It's taking all of your choices and boiling it down into a thing. In the lower right, if you've ever used an online sales tool like Amazon, and it's recommended something to you. It has basically taken your profile data and put you into a group with other customers, and it basically indicates, well, this customer would like what these other customers also liked. So this is finding the hidden groups in the data, and this is called customer segmentation. So my claim is that you have seen each of these four corners of machine learning, whether or not you have a quantitative output or not, and whether that quantitative output is categorical or continuous. And really, if you can frame your waste management question into one of these four corners, you can do machine learning with it. So I just wanted to put this out there to kind of get those gears turning. Now, again, when you have someone do machine learning or AI for you, there are some pitfalls to watch out for, and it's unfortunate, but I've seen kind of across the industry, taking these things into account is not super popular. So just simple graph on the right, let's say we have this axis, and the x-axis here is the predictor variable, the y-axis is the thing we're trying to predict. Let's say the gray data points are our empirical data, and let's say we construct a model that's this red line, and you can see it passes perfectly through the data points. It's absolutely perfect, but when it happens over here is kind of fishy. Now, this is an example of overfitting the data. Let's say we had held out some of those data. Let's say these blue dots are also part of the data set. You can see the red line does not fit the blue. Instead, this gray line would better fit all of the data. So this is kind of the fallacy of overfitting, where you expose the model to a certain data set, it memorizes the data set, and it can't abstract to new data. And this is something that's popular, especially if somebody sells you a machine learning model that's 99% or 100% accurate. Be wary and make sure they've done their due diligence. Data leakage. This is a similar idea where you have mixed your preparation. You've prepared your holdout data set and your training data set at the same time, and therefore the things applied to the one are the same as the things applied to the other. And if you don't do this properly, the model gets insider information and again can kind of memorize the patterns without actually truly learning them. Let's say you also train it on a certain customer base early on, and then over time your customer base changes. That's called data drift, where the model no longer really applies anymore, and that's something that has to be tracked by a good modeler. And then finally, this is my favorite one, because some of these machine learning models are black box problems. You have to be able to explain why it's making the decisions that it's making. So here, this is an example from the literature. The link is here, but this was a study where they trained a classifier to discriminate huskies from wolves. And essentially what they found is the prediction was occurring not because of the dog or the canine in the photo rather, but because of the snow in the photo. So it was indicating that it is a wolf because of snow and not because of the actual features of the canine. So again, if you have someone doing machine learning or AI for you, these are things that people have to account for. Otherwise, the validity of the model is suspect. So quickly, I'll show you how this can apply in the real world in a simple application. So, we're all familiar with PFAS, and PFAS can be a very tricky problem. So let's just set up a demo site here. Let's say there's multiple sources on your site, multiple kinds of things that can commingle in terms of chemistry. Let's say there's a neighboring site. They also have stuff. It is now significantly commingled with an offsite source. We think there's another site that has a source, but in reality, it's just the character of these PFAS chemicals changing on site. So we want to be able to tell that too. And then let's say we have a few locations on the site that are representative of this kind of regional ambient type of concentration. This is not due to a site impact. We'd like to know that, especially if our reference site is 10 miles away and is not really similar to the site. So this is a kind of a niche site investigation remediation question for PFAS chemistry. And you can see how complicated it gets. So quickly, I'm going to take it interactive. I'm going to share a little web-based tool that we put together internally at WSP. And the purpose here is that it does apply to waste management, but it also applies, it's just a way of showing these different concepts of machine learning, again, to kind of get the gears turning. So let's say you have your data set. This is public data from California for a landfill. But essentially, you have chemistry, and there's not an established background monitoring location. The example of clustering is divining the low stuff from the high stuff and trying to figure out what range the low stuff has. So you can see here, if we're looking at the PFOA chemical specifically, the ambient range could be up to about 7 parts per trillion, whereas the actual impacts range from 88 to 400 parts per trillion. That's a pretty clear cutoff. So this idea of clustering or finding the hidden groups can help you divine the low stuff from the high stuff. That's a pretty good application we've found. If you get into kind of source tracking and fingerprinting, that's another good application for the other corners of machine learning. So let's say, again, you have your bundle of data, you want to find the unique signals. You can use dimensionality reduction to find basically your drivers here. So here is one dominated by the PFBA chemical with lesser PFOA. This is a signature. There happens to be 3 others. And just the way this type of machine learning works, you get those profiles extracted from the data automatically, but you also get kind of this spatial gradient showing where they are more of or less of. So you can see hot spot over here grading to less of it as you radiate away. So that's an example of dimensionality reduction. Now, where people get most excited about machine learning for PFAS and chemistry is in a classifier where you've got samples from many other examples, other kinds of signatures, and you train your classifier to predict which one of those it will be. Again, this is kind of an advanced maneuver because that kind of exercise assumes that your training data are indeed representative of your site, your specific site. But this is an example of a classifier where we're trying to predict what kind of landfill versus something else the sample could be. And then where I get excited is when you change the question to, instead of predicting a signature, you're trying to understand these kind of key site-specific gradients. So here, this particular signature really increases at depth, at deeper depths to water, DTW, and it is a low concentration signature. So you can add, and if you can turn it into a number, you can use regression to do this kind of advanced correlation analysis and see how all of these potential drivers or explanatory things work together to explain your site and your site conceptual model. So with that, those are basically the 4 kinds of questions you can ask machine learning. And just as a testament to how flexible it is, those are all applied to environmental chemistry. But really, the rest of the presentation, we're going to talk about different elements of waste management. So with that, we're going to start our first poll. We're also going to switch speakers. So I'm going to hand the reins over to Nassim, and momentarily I will launch the poll.
Okay, I'm gonna start sharing my screen so Skylar has time to. Launch the poll. I see the poll.
And the poll question is, how often do you or your team use machine learning or AI? And this could be a large language model like ChatGPT. This could be a simple thing like linear regression, or it could be somewhere in between. And we'll have a kind of a corollary to this poll later on. But this is to kind of get things started. And once we'll give it another 30 seconds or so, and then Nassim, you can go ahead and take it away.
Thank you, Skylar. I appreciate the nice background that you laid for AI. What is AI and how can we use AI in our work? So it seems like everybody's done with the poll. All right, let's dive into what AI can do in waste management. And I just want to confirm everybody is seeing my screen.
Yep,
The
we can
slides.
see it.
Okay, thank you. So what is digitalization and why do we think that's a big precursor for AI? Digitalization refers to using the technology in many different ways. It can be, for example, it can be used in waste management or waste collection. When we collect the waste collection data, currently we probably use a lot of traditional paper-based system that manually then people sit and enter the data into a database. So that way we are not really efficient, data might get lost, and we just don't have a good, smooth, efficient operations. So what digitalization can help through a lot of different things. For example, Internet of Things is one aspect of digitalization. IoT, you probably have heard about it. IoT technology is becoming increasingly popular in a lot of different sectors, including waste management operations, which is basically a series of interconnected physical and actual devices, such like appliances, like your washing machine. My washing machine sends me a text when it's done. And all other objects that are connected with sensors, softwares, cameras, and all are connected through a network. Should be this your Wi-Fi at home. But it also enables real-time data. So we can collect real-time data, we can monitor our process and track. So in the world of waste management system, we can use IoT to collect data on waste generation and recycling materials from the time of collection of the waste to the recycling facility. So it can provide valuable insight on how waste is generated, how waste is managed, and what can be improved. To collect all these real-time data, we need a big repository, something central that everybody across the globe or across different geographical location can have access. So mobile and cloud-based data these days are the main storage for all these data that we collect. Can be used to create an efficient waste management operation that relies fully on not only accurate data, but also real-time data that can help us to create real-time decision-making and enhancement and improvement in our operations. So currently, only 30% of recyclable materials are recycled in the US. The remaining 70% end up in landfills and waterways. That's a sad truth, but there's a need to kind of make a modern and a smart waste management system to bridge this gap of efficiency and cost effectiveness. Digitalization can have significant benefits for us in this topic, particularly in terms of streamlining the processes and workflows by automating and digitizing processes such as scheduling and dispatching trucks. Waste management companies can often reduce the time and resources required to manage these simple yet critical tasks, which can then help to increase efficiency and productivity while also reduce cost. So now that we have a sense of real-time data and why do we need it, we can use that data to build AI-based waste management models that can be used in the waste management operations. These models rely on accurate real-time waste management data, such as waste quality, waste quantity, type, location of the waste, and also can be used to analyze the waste management data and help to enhance the recycling efforts by identifying patterns and trends that are otherwise unseen, but can inform real-time decision making. It can also help to reduce cost and substantially drive sustainable approaches that ultimately lead to climate positive operations. One of the most powerful AI tools is image recognition or computer vision. You may have already known some of these AI-based apps out there. If you're like me and love houseplants, you probably use Plant Snap or Leaf Snap to kind of diagnose your plants. I did that the other day. Or if you're a wine lover, you probably are familiar with Vivino. So some of these AI-based image recognition-based models have already been embedded in our day-to-day life. So now we have the poll number 2. We have a general understanding of AI and what needs to build an AI model. Let's take a quick poll. Use 1 or 2 words to tell where do you see AI to have the biggest impact in your work. I don't see the screen, so Skylar, if you can tell me if you have launched the poll or not, that would be great.
Yep, it is. It is live.
Okay, thank you. Thanks for sharing your perspectives. I think some of us, or maybe everybody in this meeting, have already used AI to some extent. So now let's look at how these technologies are applied in one of the most impactful sectors, waste management operation. So as I mentioned, one of the most exciting applications of AI is computer vision or image recognition. Why should we use AI in waste management operation? What are the benefits? How can you use image recognition-based technology in AI? Well, some key areas that are undergoing a massive transformation in the waste management industry include separation and sorting, waste collection and recycling, sustainability and safety. You can see the list of some of the aspects of the waste management operation that are touched by AI in this list. I'm going to dive a bit more in some of these benefits in the next few slides, but I just wanted to say that AI-based technology and application in waste management basically means a smart way to manage the waste. So we call it a smart waste management. The foundation of AI-powered image recognition basically lies in machine learning models. As Skylar mentioned earlier, machine learning models are trained using a large data sets of different data. In this case, machine learning models are trained using a data sets of labeled images, which are trained for example, to identify different types of waste, such as organic waste, like food waste versus plastics, versus metals or hazardous material. Models are exposed to thousands of images representing all these different categories. Over time, the model learns like a child to accurately recognize specific waste items based on different features like its shape, color, texture. Based on all these learning, the more data the model processes, the more accurate its predictions become. It's like in a student, the more they study, they get better in their subject. So the ability to identify and classify the waste material with precision is the driving force behind AI-powered waste management. In separation and sorting, which are one of the most complicated parts of recycling, AI technology can help to increase effectiveness and efficiency in sorting, because these are the foundation of an effective recycling. You probably are familiar with, or you heard news about rare earth metals. There are a lot of interest in recovering these valuable materials. So AI can help us to increase the recovery and make us more sustainable. It also can help to minimize the waste that is directed to landfill. So this might be counterintuitive, but it really means that the landfill life cycle is going to increase. So you're going to have a longer operation for your landfill. Another AI tool that can help and be used in separation and sorting is robotic recycling and sorting. So basically using robots with advanced cameras to sort through the waste by increasing safety, to minimize human and environment exposure with dangerous materials. So if you have robots do screen the waste, that helps to reduce the human exposure to potential toxics. It can help. They can also help to continue to have a continuous operation, which can ultimately lead to faster processing time. Robots can also help to minimize human decision-making errors, and therefore having more reliable and agile operations. Driving sustainability and ensuring more materials are recovered, reused, and repurposed is another benefit of using AI-based models in sorting and handling waste. These all can help us to build and move towards a more circular economy. Another benefit of smart waste management is making waste collection more efficient. If you recall earlier, I talked about Internet of Things, IoT, which is basically applying machine learning to real-time sensor data. Internet of Things have been enabling us to create smart bins that are kind of revolutionizing the waste collection in a lot of cities across the world. They're basically equipped with a sensor that can measure waste level, it can detect odors, and it can also monitor the bin status. These smart bins provide real-time data to waste management operators. These data can then be stored and processed in a centralized system that can monitor waste levels across the city. It can allow for an efficient scheduling and allocation of resources. For example, sensors within a smart bin can detect the bin capacity, and it can automatically alert collection services to dispatch a truck to empty the bin. Use of IoT and smart sensors can help to increase operational efficiency, as I explained earlier, but also can cut cost and enable or enhance customer satisfaction. How can IoT help us to do this? By route optimization, minimizing missed pickups, minimizing unnecessary pickups, enabling waste generation and analysis to forecast future waste, future load, and potential opportunities for recycling. And can also help to decrease the driving distance and further contributing to reduced emissions. So implementing IoT technologies and IoT-based system for waste management can achieve up to 25% reduction in overall cost. Some literature report more of a range between 12 to 30%, but we can all understand how IoT-based technology can reduce the cost in waste management. So smart waste management also enables a predictive analysis, which can be game-changing. Predictive analysis can be game-changing because they're moving us from reactive to proactive management. AI algorithms can analyze the IoT generated real-time data, not only to predict the waste pattern, but also dynamically adjust the collection schedules and optimize resource allocations. Inventory and optimization for assets and resources can be done by optimizing truck routing, bin distribution, and manpower allocation for each collection system. It can also minimize the idle vehicles, so they don't need to kind of waste the fuel. We can also use them for other predictive users. We can use them for tracking landfill gas or forecasting the gas, recycling performances, even anticipating climate impacts in events of floods or storm that can affect waste infrastructure, waste collection. So it can also help to minimize accidents and enhance safety by eliminating unsafe or due for change parts. It can also help to identify hazards and come up with prevention plans. But I wanted to mention that AI should support, not replace human judgment, because as Skylar mentioned earlier, it's very important to use a team that understands nuances and can, prevent from fatal errors. A team that's fully capable to use appropriate judgment in building AI models. Oops, sorry. So another big area where AI and machine learning can make an impact is recycling. Enhanced sorting accuracy by giving us a vision system that can identify and separate materials more precisely, reducing contamination and increasing recovery rate. It can also help to create a cleaner recyclable stream, fewer rejected items, fewer rejected loads, and more materials basically staying in use and in the economy rather than going to landfill. Automation can also help to speed up operations, but reduce worker exposure to hazardous waste. Another way that AI can help is to help optimizing recycling facility logistics, improving processing time, and supporting a greener economy in general. So the result is less waste, more resource recovery, and lower carbon emissions from the entire process. Here is an example or a table basically showing some of the cities across the globe that have used IoT devices and technologies, mainly have used them for household waste collection across the world. But you can see some of the cities, countries, for example, Qatar has used IoTs in making smart trash bins, but it has been applied and it's been used in some level. So far we have seen how digitalization and AI and ML can transform waste management operations, improving efficiencies, safety, improving recycling. But these improvements don't just make the operation smarter. They directly connect to a much bigger challenge that they're facing, climate resiliency. So let's step back and look at the big picture. AI and machine learning models aren't only operational tools, they are becoming essential for helping us to cut emissions, adapt to climate shocks, and move towards a more circular economy. Carbon footprint reduction can be one of the features or aspects that AI can help by applying smarter routes, optimizing the operation, which means fewer miles that trucks have to travel, lower fuel spent, and lower CO2 emissions. Models can also help to capture more landfill gas and divert organics away from landfills. AI can help a circular economy by improving recycling accuracy. It can make it possible to keep more resources in use, and as I mentioned earlier, and out of disposal. Predictive analytics also help us to faster respond after an emergency, after a storm, flood that can disrupt the waste stream. AI can also help to extend the life of facilities and equipment by predicting the maintenance due earlier and reducing replacement emissions. And critically, AI can support ESG, environmental social governance, and net zero targets by providing the data that need to track the progress. So in summary, machine learning and AI have already been used across the waste management lifecycle. There are a lot of different opportunities that I didn't even get a chance to touch on today. ML and AI models require a capable team to develop and deploy, but are not prohibitive. And AI doesn't just make waste management faster and it makes it safer, cheaper, and much more climate resilient. With that, I'd like to end the presentation and open the floor to questions.
Awesome. Thank you, Nasim. Yeah, folks, if you'd like to ask any further questions, chat is still open. We've got a couple of questions to start us off. I guess if you had to pick one area of AI technology that you talked about towards the end, Nasim, which would you say might be the most promising?
I would say route optimization. have the most what do you say, capacity for being more efficient. It can help the trucks do a better job, do a more efficient way to collect trash. And sometimes, I don't know about you, but I was walking the other way and I saw, the trash smell. I felt this trash smell. So if you can do a better collection service using AI, that can help customers and give a more pleasant experience, giving the residential area a more pleasant environment to live in, it would be that area basically.
Great. And using that Internet of Things, that kind of sensor-based approach too, where you've instrumented vehicles and you can tell which routes are optimal or how to improve that routing. Very cool. Another question, do you have any recommendations for starting to implement AI solutions on projects? Like, let's say currently all judgment is manual and certain calculations, maybe there's certain kind of screening level calculations performed, but to shift into kind of an AI mindset and start using some of these tools, do you have any recommendations for just getting started?
So I think there are a lot of tools out there. I would just caution everybody to use a good judgment. Do not fully trust any AI model out there, because they're not you. They don't have the knowledge that you have and experience that you have. So I would caution everybody that even if you use whatever tool that you use, there are a lot of tools out there, right? I think between you and I think we shared about 20 different apps that can be used for day-to-day life. But use your judgment also. Do not fully trust the result of an AI model blindfolded, basically.
Right. So using judgment and still kind of using AI as like a decision support rather than like a complete decision takeover. Yep,
Right. Do
I hear
not
that.
put the AI in the driving seat per se.
Got it.
Yeah.
I guess one thing that comes to my mind as well is the idea that it's okay to start small too. Like, if you've got an area that you'd like to improve in and you've got data that fit one of those four categories we talked about earlier, smaller, simpler approaches can be a really decent way to pilot some approaches and just see what sticks, see if it actually adds value, and you don't have to go straight into this gigantic cloud deployment with spending money on telemetry or sensors necessarily. You can start small and kind of pilot some methodologies and see what works best for the team. So
Right. I mean, I think we do take the similar approach in the water world, for example. We don't jump into designing a full large scale 100 MGD plan. We start from bench top study and then we move to a piloted study. So we build step by step we don't fully submerge into the, like you said, large model which can cost a lot of money.
right. Okay, we've got Linda. All right, yes, this is a good reminder too. If you would like a certificate for the 1 hour PDH, please contact Linda. There's her email. And if any of these ideas or concepts are of interest too, we'd be happy to talk with people offline later and connect with one of our WSP data science teams. I guess for remaining time, if anyone has any questions, happy to open the floor. Folks are welcome to come off mute, ask questions or anything. Otherwise, we can give people a few minutes back in their day. So we'll leave it open for a couple more minutes, but at this point, we'll just thank everyone for attending, and yeah, it's been a pleasure. Looks like we do have some action in the chat. Okay. Yannick, go ahead. Oh, I see the Q&A. Very good. All right. For the engineering, consulting, business aspects, landfill monitoring data in particular, would you train models on limited client data or a range of landfills and clients? By restricting data, it limits the accuracy of your AI, but there's also confidentiality issues. So yeah, getting at that idea of large data versus site-specific data versus generalizable data to be able to make models. Nassim, would you like to take first crack at that one?
Sure, I would say that depends on the application and what is your objective here. If you can't share, first of all, I don't think we necessarily need to expose clients' information in the data. But if you need to expose client data, yeah, we can't really, you're gonna build your model on your limited available data. But if your objective is not exposing your client's information, for example, you're building a model on to predict the methane emission or gas emissions from landfill. I don't necessarily think you need to expose the landfill name, but if you do, then I would recommend to just focus on your limited data from your client and then test it on a bigger range of landfills. What do you think,
Right.
Skylar?
Yeah, it definitely gets back down to legal, legal everything, right? So I guess in turn, kind of default answer is that kind of mixed data sets, you don't mix and match, and you don't ever make anything public facing that's not already legally public facing. So really, if you've got and that does get into the world of AI, right, where tech companies have all of our data. We're the clients. Every one of us is a client in the tech industry, right? Because we're all consumers of their stuff, and they do use all of our data to make predictions and inferences, and that can be contentious. So at least in our industry, the idea being, if you're going to make a machine learning model of some kind, like operate within a portfolio, right? If this is a model for a client, let's set up the right details to use like the portfolio wide data, if that's deemed legally appropriate. If we're going to do something that kind of operates on a larger scale and is going to be kind of agnostic to the client base, that's where public data come into play, or you kind of transfer the learning from like a public setting, from publicly available information into a site-specific setting. So yeah, I would say that's definitely something always to be considered with legal. But then, so let's say, I'd say portfolio-wide solution or a solution based on like a large public repository. Both of those are generally by default okay. But I would say site-specific solutions too are underrated. Like if you're trying to do forecasting or Internet of Things, like that's based on large sensor records from your site, and those can be forecasted without a large external data set as well. So there's kind of really there's really three scales you can operate at that are generally pretty appropriate. Cool. Thank you, everyone.